Tonight, we're going to explore one of the most quietly unsettling questions in modern space science. Not whether humans can reach Mars, but whether anyone could actually live once they got there. The fantasy is familiar. Domes on red plains, children born under a smaller sun, a second home for our species waiting just across the dark. But the real Mars is worse than almost anyone imagines, and the reason is hiding in a single word everyone gets wrong: atmosphere. Mars has one. That's the part that fools people. What they don't realize is that it's barely there, about 0.5% as thick as the air above your head right now, and almost pure carbon dioxide. The pressure is so low that an unprotected human wouldn't suffocate slowly. They would lose consciousness in about 15 seconds and be dead in under 2 minutes. Not from cold, not from lack of air, from physics most people have never heard of. By the end of tonight, you're going to understand why that thin shell of carbon dioxide makes the surface chemically uninhabitable, what the Armstrong limit does to a living body, and what it truly means to call a sealed machine on an indifferent planet a home. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. It's true, Mars has an atmosphere. People hear that and picture something useful, something that softens the edge of exposure, holds a little warmth, carries a little weather. The word atmosphere lands in the mind the way it does on Earth, where the atmosphere is a thick, life-sustaining blanket pressing down from above, with enough force to keep water liquid and lungs working. But here's where it gets strange. Mars's atmosphere is not thin in the way mountain air is thin. It is not the kind of thin where you breathe harder and slow down and eventually acclimatize. It is something else entirely. The pressure at the Martian surface is roughly 0.6 kilopascals. Earth's sea level pressure is about 101 kilopascals. That is not a modest shortfall. That is a pressure so low it has more in common with the near vacuum of high orbit than with anywhere a human being has ever breathed. If you want an altitude comparison, the Martian surface sits at the pressure equivalent of roughly 100,000 feet above the Earth. That is not the summit of Everest. The summit of Everest is around 29,000 feet. This is more than 3 times higher than that, into a region where no aircraft cabin could keep you alive, and no amount of adaptation buys you another minute. The density of the Martian atmosphere is about 0.6% of Earth's at sea level. Not 60%, not 6%, 0.6%. There is a threshold in aerospace medicine called the Armstrong limit. It sits at roughly 63,000 feet above Earth. At that altitude, the pressure has dropped so far that water boils at 37 degrees Celsius. That is human body temperature. What that means is not simply that the air gets cold or that breathing becomes difficult. It means that the physics of water changes at the temperature of living tissue. Above the Armstrong limit, the moisture in your mouth, the fluid on your eyes, the damp surfaces of your lungs, the liquid in your blood and tissues no longer needs heat to vaporize. It just needs the pressure to be gone. And the pressure is gone. Mars sits far above the Armstrong limit. The entire surface does, everywhere, all the time. What happens to an unprotected human body exposed to the Martian surface is not slow. It is not a gradual weakening. The moisture in the mouth and eyes begins to vaporize within seconds. The lungs cannot draw any useful breath. Consciousness is gone in roughly 15 seconds. Death follows in under 2 minutes. This is not theoretical. Altitude chamber data collected over decades of aerospace research confirms the sequence. It happens that fast, and there is no intervention that changes it because there is nothing to intervene against. There is only the absence of pressure. The common image of exposure on Mars, the suited explorer who trips and cracks a visor or loses a glove, captures something real. The suit is not equipment. The suit is the condition of being alive. But wait, even if the pressure were somehow workable, the air itself would kill you first. The Martian atmosphere is composed of roughly 96% carbon dioxide. About 2.6% is nitrogen. About 1.6% is argon. Oxygen, the gas that sustains every breath you have ever taken, makes up approximately 0.16% of the Martian atmosphere. Earth's atmosphere contains about 21% oxygen. The difference between those two numbers is not a matter of degree. It is the difference between breathing and not breathing. Carbon dioxide is not simply unhelpful. Above about 5% concentration in a breathing mix, it is directly toxic. It causes headaches, confusion, rapid loss of consciousness. The Martian atmosphere is 96% carbon dioxide. If you took a breath of Martian air, the CO2 would begin poisoning you before the lack of oxygen had a chance to do anything. You would not suffocate slowly. You would lose consciousness almost immediately, not from starved lungs, but from a gas that the body treats as a signal of crisis at concentrations 1/20th of what Mars offers with every breath. This matters because it closes every door at once. The pressure alone kills. The composition kills. Each one would be independently fatal. Together they produce a surface environment that has no parallel in ordinary human experience. Antarctica is cold. High mountains are thin. Remote deserts are brutal. But all of those places share a single feature that Mars does not. You can breathe there. Not comfortably, not forever, but you can stand on the ground and draw a breath that does not kill you. On Mars, you cannot. There is no duration of adaptation, no biological toughness, no acclimatization process that moves the dial. This is the principle that every other fact about Mars rests on. You cannot live on Mars. You can only live inside something on Mars. That distinction is not a technical detail to be filed and forgotten. It is the central fact of Martian existence. The boundary between life and death on Mars is not a mountain range you do not cross. It is not a weather system you shelter from. It is a wall, a physically engineered wall, pressurized to hold roughly 101 kilopascals of breathable gas against a surrounding environment, pressing back with 0.6. That wall has to hold. It has to hold while you sleep, while you work, while someone makes a repair in the corridor nearby, while a dust storm outside runs for weeks. The moment it fails to hold, the sequence that begins in 15 seconds begins. Think about what that means for the mental image of Mars as a frontier. A frontier implies that you step outside and survive. You endure cold, distance, hostile terrain, but you can step outside. You can feel the planet under your feet without a machine standing between you and it. Nothing about the Martian surface permits that step. Every version of life there, every meal, every conversation, every night of sleep, every moment of illness, every argument and every quiet hour happens inside the container. The container is not where you live on Mars. The container is the only place that exists. That single engineering fact reshapes everything else. And it was only the beginning of what makes the Martian surface so different from the picture we carry. So step through that wall for a moment, not to cross it, just to understand what it actually is. Most people imagine a Mars habitat as a base, something solid, 4 walls, a roof, a door. The picture is of a structure built the way a structure is built on Earth, anchored to the ground, sheltered from the weather, fundamentally inert. That picture is wrong. Not slightly wrong. Fundamentally wrong. What the habitat actually is, structurally, is a pressure vessel. A sealed container holding pressurized gas against an environment that has almost none. At Earth standard internal pressure, roughly 101 kilopascals, the outside atmosphere pushes back with 0.6. That differential is enormous. Every single square meter of habitat wall is being pushed outward by approximately 10 metric tons of force. Think about that. Not on the whole structure, on every square meter. The habitat is not a box sitting calmly in the landscape. It is a balloon, held in shape by the gas inside it, against vacuum that wants to pull every seam apart. Lower pressure designs, running around 52 kilopascals with oxygen-enriched air, reduce that outward force. But they introduce fire risk and complicate the balance of breathing gases. Most working designs aim for something between 70 and 101 kilopascals, which means the outward pressure on the walls stays large. It stays large every hour of every day that anyone lives inside. This matters because it changes the nature of every failure. On Earth, a crack in a wall is a structural problem. On Mars, a crack in a wall is a countdown. A hairline fracture the width of a human hair, in a joint, a seal, a window frame, is enough to whistle pressure out of the interior. Not instantly, over hours, but at a rate that, left unrepaired, drops internal pressure to levels where consciousness goes first and death follows. A larger breach, a failed seal, a micrometeorite puncture moves that timeline from hours to minutes. Compare that to the best case we have for managing pressure leaks in a sealed habitat. The International Space Station has experienced small pressure leaks, and finding and sealing them required weeks of painstaking detective work. With full ground support, a large engineering team on Earth running real-time analysis, and every spare part accessible by a resupply mission within months. On Mars, none of those conditions exist. And Mars adds stresses that a station in the relative stability of low Earth orbit does not have. The surface temperature swings roughly 65 degrees Celsius between night and warm equatorial afternoon, from around -70 at night to roughly -5 on the warmest days. Every one of those cycles expands and contracts the seals and joints in the habitat walls. Every single one. And Martian dust is electrostatically charged, abrasive, and fine enough to work into every gap, every surface imperfection, every crevice around a seal. The thermal cycling weakens. The dust infiltrates. Over months, over years, the probability of a failure compounds quietly. But the picture does not hold. The distance to Earth at any given moment ranges between 55 million and 400 million kilometers, depending on where the two planets are in their orbits. A one-way communication signal takes between 4 and 24 minutes to arrive. A two-way exchange, the absolute minimum for any real conversation, takes at least 8 minutes. On a bad orbital alignment, nearly 50. A crew member wakes at 2 in the morning to an alarm. A seal is failing. Air is leaking into the Martian sky. There is no emergency call, no evacuation, no rescue team en route. A distress message sent to Earth will arrive, at minimum, 4 minutes later. The reply, from engineers who cannot see the hardware, cannot touch the seal, cannot do anything except talk the crew through what their hands are already trying to do, will arrive at minimum 8 minutes after the original message, while the pressure drops. This is not the description of a crisis scenario. This is the description of baseline life on Mars. The possibility is not rare or unlikely. It is the permanent condition of living inside a balloon surrounded by near vacuum, on a surface where the nearest help is measured not in kilometers, but in light minutes and orbital mechanics. Now, consider what that balloon actually contains. A reference design from NASA-style work, the CHAR analog developed at the Johnson Space Center, puts the pressurized living volume for a crew of 4 at roughly 158 square meters, about 1,700 square feet, the size of a modest 2-bedroom apartment. That same volume must also contain sleeping quarters for 4 people, a kitchen, an exercise area, a medical bay with surgical capability, a laboratory, a food growing section, water recycling hardware, and the air processing machinery that keeps everyone alive. There are no hallways leading to other rooms in other buildings. There is no other building. There is this. Visiting a neighboring habitat, if one exists nearby, is not a matter of stepping outside. It is a logistical operation. Pressure suit, donned fully and checked. Airlock cycle, which takes several minutes. An exposed traverse across a surface where the temperature averages -60 degrees Celsius, where polar regions in winter approach -125, where the warmest moment on the warmest equatorial day barely reaches 0. A second airlock on the other side. Repressurization. The whole sequence reversed on the way back. What on Earth would be walking next door takes 30 minutes on Mars, and requires a machine standing between you and the planet at every step. Inside the habitat itself, the conditions accumulate. You eat in the same room where you work. You sleep within arm's reach of life support machinery. The exercise area is a corner with a treadmill facing the same wall you faced yesterday, and the day before. Privacy is measured in cubic feet, not rooms. 4 people share roughly the floor space of an apartment designed for 2. And there is the sound. Fans moving air through the scrubbers, pumps cycling water through the recycling system, compressors, heat exchangers. The habitat is never silent. It cannot be. Silence on Mars does not mean quiet. Silence means life support has stopped. After a week inside, you know every scratch on every surface. After a month, you know the rhythm of every mechanical cycle, which pump comes on when, which fan changes pitch at what hour. After a year, the walls do not feel like they are closing in as a metaphor. They feel like it because perceptually, they are. The space does not change. The human nervous system, built to range across open landscapes, has nowhere to range. The exterior of the habitat seals against winds of 60 to 100 kilometers per hour. At those speeds on Earth, that is a strong to severe wind. On Mars, because the atmosphere is so thin, a 100 kilometer per hour wind hits you with roughly the force of a light breeze. Almost no physical force. You would barely feel it. But the wind carries dust, and dust on Mars is something else entirely. So you go outside. After months sealed inside those walls, the airlock finally cycles and the door opens, and you step through it onto the surface of Mars. Surely that is the relief. Surely that is the reward. Open space after confined corridors, a horizon after a ceiling, the planet itself after the machine that contains you. But the relief does not come, because outside is not outside. Not in any way a human body has ever meant that word. The suit you wear is not what the movies show. It is not a sleek fitted garment. It is a pressurized, multi-layered system built to maintain its own internal atmosphere against a world trying actively to destroy it. Thermal insulation against temperature swings that would freeze unprotected skin in minutes. Radiation mitigation layered into the fabric. Dust-resistant seals on every joint and coupling. On Earth, that suit weighs between 40 and 70 kilograms, roughly the weight of another person strapped to your body. Mars gravity reduces the effective weight to 15 to 27 kilograms, but you still feel it. Every movement works against the pressurization stiffness, against the joint constraints, against the resistance of a wearable spacecraft that does not want to bend. Before you even reach the airlock, you have spent 30 to 60 minutes putting it on. Pre-breathing protocols first, to prepare your blood gases for the pressure difference between the habitat and the suit, and avoid the same decompression sickness that plagued deep-sea divers for centuries. Then the layers, the checks, the seals, then the airlock cycle itself, pressure bleeding down, the outer door releasing, and then you are outside, and a countdown has already started on your oxygen supply. A torn glove seal, a cracked visor, a jammed joint that locks your arm. Any one of these does not mean discomfort. It means minutes, not hours, minutes. And even out there, waddling across the rust-colored ground with that countdown running, you are not touching Mars. You are inside something. You are always inside something. The wind moves around your suit and you cannot feel it. Not on your skin. The Martian atmosphere is too thin to carry heat away from an exposed hand or cold into an exposed face. The sensory exchange that every previous frontier offered, the bite of polar wind, the sting of desert sand, the cold salt spray on an ocean crossing, is structurally unavailable. The planet surrounds you and you feel none of it. You cannot touch the soil. Bare hands on Martian regolith would mean bare hands in near vacuum, and that toxic, electrostatically charged dust against unprotected skin. You press a gloved boot to the ground. You register pressure through rubber and insulation. That is as close as your nervous system ever gets to the planet underfoot. You cannot smell the air. There is no breathable air outside the suit. There is nothing to inhale but what the suit provides. And the silence. The Martian atmosphere is so thin that it carries almost no sound. An unprotected ear on the Martian surface would hear barely a whisper of the world around it. The wind that lifts dust across hundreds of kilometers, that sculpts the terrain and moves the landscape, arrives at the human ear as nearly nothing. A ghost. You can watch the dust devils spinning in the middle distance, visible, real, and hear almost no trace of them. Think about every frontier in human history. The cold on the faces of the men crossing Arctic ice, the sand between the fingers of desert travelers, the salt on the lips of sailors weeks from shore, waves striking the hull at night. Sensory experience was not incidental to the frontier. It was the substance of it. The body knew it had arrived somewhere new because the world pressed back against the body. That pressing back was the whole thing. Mars denies this, completely and permanently. You could spend an entire lifetime there. Years of walking those rust-colored plains, watching those ochre sunsets, traversing the flanks of mountains and the rims of craters, And in all of that time, there would never be one single moment of standing on the planet the way a person stands barefoot on a beach, or faces into a forest wind, or puts a hand in cold river water. The planet is always right there, inches away on the other side of a visor, and it stays there. You traveled roughly 225 million kilometers to reach it, and you experience it entirely through layers of glass, rubber, fabric, and pressurized air. Not a destination arrived at. A destination observed from inside a series of nested enclosures that got slightly larger when the airlock opened. Here's where it gets strange. The images do not tell you this. The images from Curiosity and Perseverance look like the American Southwest. Reddish rock, sandy plains, distant mesas, low clouds at dusk. Your brain processes those images exactly the way it processes a photograph from Arizona or New Mexico, and it reaches a conclusion. Harsh, but recognizable. A very cold desert. A high mountain plateau. Difficult, but the kind of difficult a human being can endure if properly equipped. That conclusion is wrong. Not slightly wrong. Categorically wrong. The driest place on Earth, the Atacama Desert in northern Chile, still has breathable air above it. You could stand in the Atacama in ordinary clothing and survive the atmosphere, even if everything else tried to kill you. The summit of Everest, at roughly 8,800 meters, still has enough atmospheric pressure to keep the blood liquid in your veins. Climbers suffer terribly up there, but their blood does not boil. And the coldest winter on the Antarctic plateau still occurs under a magnetosphere, under an ozone layer, inside a protective envelope, that deflects the radiation streaming in from the sun and from deep space. Mars has none of these, not one, not a partial version of one, none. The terrain looks like a desert you could survive in. It is a vacuum chamber shaped like a desert. The geological similarity is real. The biological similarity is zero. So there is no open frontier on Mars, no wilderness to explore in the way that word has ever meant anything. What exists instead is carefully planned excursions, time limited by oxygen, physically exhausting, conducted in risk-laden suits where a single failure cascades toward death in minutes. What exists, instead of a sky above your head, is always a ceiling. Large windows, the kind you might imagine wanting in a place with sunsets like those, are structural vulnerabilities and radiation entry points. Radiation passes through ordinary glass nearly unimpeded, so the planet is seen mostly through small reinforced viewports, or through camera feeds, or not at all. The surface is not a place you live on. It is a place you shelter from, behind walls of metal and regolith and recycled air, emerging briefly and at cost. The atmosphere, the pressure, the cold, the dust, these are the dangers you can feel or would feel if you were exposed to them. You can picture them. You can imagine what they would do to an unprotected body, because your senses have reference points for cold and pressure and particulate and wind. What comes next has no reference point at all. The next danger is invisible, silent, unfelt, accumulating inside the body without a single signal that it is there. Start with what protects you at home, because until you understand what Earth provides, you cannot feel what Mars withholds. Right now, without any awareness of it, you are being shielded by two systems. The first is the magnetosphere. It is a vast magnetic bubble generated by Earth's churning liquid iron core, extending tens of thousands of kilometers out into space, bending charged particles away from the planet before they ever reach the upper atmosphere. You cannot see it. You cannot feel it. You have never once had to think about it. But it has been deflecting the worst of deep space and the sun's outflow for billions of years, quietly, without interruption. The second shield is the atmosphere. That column of gas, roughly 100 kilometers deep, does not just carry the air you breathe. It absorbs and scatters most of the high-energy radiation that makes it past the magnetic field. What gets through after both shields have done their work is a natural background dose of about 2.4 millisieverts per year. A millisievert is a unit measuring the biological effect of radiation on tissue. The average American absorbs about 3.1 millisieverts per year, slightly higher because of medical imaging and other sources. A chest X-ray delivers about 0.1 millisieverts. A full-body CT scan delivers about 10 millisieverts. At 2.4 millisieverts per year from the environment alone, your body handles the dose effortlessly. The repair mechanisms inside every cell were built for exactly this. It is biologically trivial. Mars has neither shield, not weakly, not partially, effectively not at all. About 4 billion years ago, Mars's core cooled. When it cooled, the internal churning that generates a global magnetic field shut down. The dynamo stopped. The magnetosphere collapsed. What remains today is scattered, weak, remnant magnetism frozen into the rock of the southern crust. It protects nothing meaningful. A habitat, a crew, a square kilometer of surface, none of these receive any useful deflection. Mars is, for all practical purposes, magnetically naked. The thin Martian atmosphere stops some low-energy solar particles at steep angles. Against the most dangerous high-energy radiation, it is nearly transparent. So everything that would have been deflected or absorbed by Earth's two-layered system arrives at the Martian surface largely unimpeded. In 2012, the Curiosity rover began measuring the surface radiation environment with an instrument called the Radiation Assessment Detector. It has been measuring continuously ever since. The number it returned was not what most people picture when they imagine walking on Mars. The annual surface dose from galactic cosmic rays alone is between 240 and 300 millisieverts per year. That is roughly 80 to 100 times the natural background a person receives on Earth every year, with no way to turn it off, no shelter season, no low exposure window, no part of the calendar when the number drops. But the name is misleading. Galactic cosmic rays do not behave the way the name suggests. The phrase sounds like something moving through space the way visible light does. It sounds like a wave, like a glow, like something that warms or illuminates. That intuition is wrong. Galactic cosmic rays are not rays at all. They are particles, mostly protons, but also something more destructive, heavy atomic nuclei of elements like iron, silicon, and carbon, accelerated to significant fractions of the speed of light by supernovae and other violent galactic processes. These are called HZE particles, for high charge and high energy, and the way they interact with living tissue is nothing like the way an X-ray passes through. Think about what an X-ray does. It passes through soft tissue largely without interaction, which is why it casts a shadow on a detector and lets a doctor see a bone. The ionizing damage is real, but diffuse. An HZE particle does something different. When a heavy, fast-moving iron nucleus enters tissue, it carves a dense track of ionization through every cell in its path. Imagine a microscopic meteor punching through layer after layer of cellular structure, not the faint trace of an X-ray. A concentrated corridor of disruption, cutting through hundreds of cells in a single pass. Every cell that track crosses has its chemistry disturbed. Misrepaired DNA is how cancer begins. The particle does not slow down appreciably. It passes through and is gone, and the damage it leaves behind is structural and molecular at the same time. On Earth, the magnetosphere and atmosphere stop almost all of them before they arrive. On Mars, they arrive at about 0.7 millisieverts per day. That is the ambient background of interplanetary space, delivered to the surface because nothing stops it. It does not cycle with the seasons. There is no peak and no subsidence. It is simply the environment. And then there is the second threat, different in character, potentially more immediately dangerous. Solar particle events are sudden intense bursts of energetic protons thrown outward by solar flares and coronal mass ejections. They are less constant than galactic cosmic rays, but far more concentrated over short periods. A major solar particle event can deliver hundreds of millisieverts in a matter of hours. Without shielding, a severe event delivers enough dose to cause acute radiation syndrome. That means nausea, vomiting, immune suppression, and in extreme cases, death within days or weeks. The MAVEN orbiter confirmed that solar particle events strip material directly from the Martian atmosphere during these episodes. The atmosphere itself is being eroded in real time. The surface, meanwhile, receives the full proton flux. Now the math. NASA standardized its career radiation limit for astronauts in 2022. The limit is 600 millisieverts total across a career, regardless of age or sex. The limit is set to correspond to a 3% increase in the risk of cancer-induced death at a 95% confidence interval. That is the agreed threshold at which the risk becomes unacceptable by institutional standards. At 240 to 300 millisieverts per year from galactic cosmic rays alone, a person living on the Martian surface hits that career limit in roughly 2 to 2.5 years. That number does not include the transit dose. Getting to Mars takes 6 to 9 months each way. The journey itself, traveling through interplanetary space with no planetary magnetosphere overhead, adds to the total before the first day on the surface is counted. A 2013 study published in the journal PLOS-1, using NASA's own risk models, calculated central estimates for radiation-induced mortality on a Mars mission above 5%, with upper confidence intervals approaching 10%. Radiation-induced morbidity, meaning serious illness short of death, was estimated above 10% centrally, with upper estimates near 20%. These are not worst-case figures generated by alarmists. They are institutional models applied to the radiation environment we have actually measured. And that is the part we can quantify. Here is the part we cannot. HCE particle exposure may additionally affect the central nervous system in ways that do not yet appear in any biological dataset, because no human being has ever accumulated long-duration exposure to this environment. The concern is not theoretical. Laboratory studies with animals show cognitive effects from HCE exposure. But the long-term consequences for a human brain subjected to years of heavy nucleus bombardment cannot currently be predicted. We do not have the data. We are proposing to send people into a radiation environment whose neurological consequences remain genuinely unknown. People imagine the Martian surface as a landscape to walk through. A difficult one, a demanding one, but a landscape. The radiation data changes that picture. The surface is an ongoing emergency-grade exposure environment, even on a completely calm day, with no solar event, no storm, no exceptional circumstance. Just an ordinary quiet afternoon in the Martian afternoon light is already a dose that accumulates toward a career limit in 2 years. The radiation is not a risk event, it is the baseline. That baseline never stops. So the answer seems obvious. If the surface irradiates you, go below it. Put rock between yourself and the sky. The deeper, the better. Bury the habitat, seal it in regolith, and the problem becomes manageable. That instinct is correct in its general direction. But Mars complicates even that. A 2022 study published in the Journal of Geophysical Research modeled what actually happens to radiation dose as you descend beneath the Martian surface. The researchers expected a simple curve, more depth, less dose. What they found was something different. The effective dose does not peak at the surface. It peaks at roughly 30 centimeters below it. A thin layer of dirt is worse than no cover at all. Here is what happens. When high-energy galactic cosmic rays strike regolith, the loose rock and dust of the Martian surface, the collision produces secondary particles, primarily neutrons. Those secondary neutrons scatter in all directions, including downward. They spread into the shallow zone just under the surface. So a person sheltering under 30 centimeters of regolith is receiving both the original primary radiation coming from above and the secondary neutron field generated by that same radiation hitting the dirt around them. Think of it like shrapnel. The initial impact is dangerous, but the fragments it throws in every direction can be more dangerous still. The thin covering does not protect. It adds to the problem. Beyond that 30 centimeter zone, the dose begins to drop steadily, but not quickly enough to matter until the depth becomes substantial. Safe long-term habitation, defined as an annual dose below 100 millisieverts per year, requires between 1 and 1.6 meters of regolith overhead. At 2 meters, the dose drops to levels considered acceptable across a working career. At 3 meters or more, it approaches something close to Earth's natural background radiation, dramatically better than the surface, not incrementally, but only at those depths. Anything shallower than 1 meter buys almost nothing. This means any permanent Martian habitat requires one of two things. Either it is buried under at least 1 to 2 meters of crushed rock, or it is built inside a natural geological feature that already provides equivalent mass overhead. Mars has exactly that kind of feature: lava tubes. These are tunnels formed by ancient volcanic flows, hollow channels left behind after the outer crust of a lava river cooled and solidified while molten rock drained away beneath. Orbital imagery has identified them across the Martian surface. Some may be hundreds of meters in diameter, not narrow passages, spaces large enough to contain entire pressurized structures, with room to move, with roofs already in place. Multiple research groups and space agencies have proposed lava tubes as the most promising sites for early human settlement. The shielding mass is already there, no construction required to achieve it. But there is a catch. We have seen lava tubes from orbit. We have not seen the inside of a single one. Their interiors are uncharted. Their structural integrity after billions of years of thermal cycling, seismic stress, and meteorite impacts is unknown. A roof that has survived 4 billion years may be stable indefinitely, or it may be one moderate impact away from partial collapse. We do not know. A partial roof collapse inside a pressurized habitat is not an engineering problem to solve over several hours. It is a catastrophic, immediate failure. And the terrain access to lava tube entrances is typically steep and technically demanding, which complicates the question of how to get there in the first place, carrying everything required to establish a settlement inside. The alternative is simpler to understand and harder to build. Surface habitats buried under regolith dig, transport, and place 1 to 2 meters of crushed rock over the top. Straightforward in principle, but 1 to 2 meters of regolith over a habitat large enough to sustain a crew means moving hundreds of metric tons of material. In some configurations, thousands. That requires heavy autonomous machinery. It requires reliable power to run that machinery continuously. It requires months or years of robotic preparation before the first human ever sets foot on the surface. The habitat does not exist until the rock is in place. The crew cannot arrive until the habitat exists. Either way, there is no version of long-term Martian life that takes place above ground. And here is what that means for the image that draws people to Mars in the first place. The domed city. The panoramic habitat with great curving windows looking out across rust-red plains toward a pale sky. The view that makes the sacrifice feel worthwhile. Glass offers no protection against galactic cosmic rays. Neither do transparent polymers. Neither does any material that allows light to pass through it. Because the physical properties that make a material transparent are incompatible with the mass and density required to stop high-energy particles. A large window is not a feature of a Martian habitat. A large window is a radiation entry point. The romantic domed city is not just architecturally difficult or logistically challenging, it is radiologically suicidal. Every hour spent near that window is cumulative dose, moving toward a limit that cannot be undone. Water helps somewhat. A layer 20 to 30 centimeters thick acts as a meaningful moderator for neutrons, and for the lower energy protons released during solar particle events. Dense metals block some of the lower energy radiation, but water is heavy and metals are heavier, and every kilogram launched from Earth carries an enormous cost. These are supplementary tools, not solutions. The solution is depth and mass. The consequence is darkness. What Martian life actually looks like is this: a heavily shielded inner sanctum for sleeping and extended rest, where the mass overhead is greatest, work areas with lighter shielding, used for shorter periods, with time carefully rationed, and a spreadsheet, not a metaphor, an actual running total for every member of the crew, tracking cumulative absorbed dose against a lifetime allowance that cannot be extended once reached. Every inhabitant tracks their dose the way a person managing a serious metabolic condition tracks blood chemistry, constantly, carefully, with the knowledge that going over the limit carries irreversible consequences. Outdoor excursions are not limited only by how much oxygen the suit carries or how physically tired the person becomes. They are limited by radiation budget, a weekly ceiling of hours outside shielded zones. The medical officer keeps the ledger. Each sortie, each hour in a lightly shielded corridor, each solar storm caught in the wrong room, all of it enters the record. The particular cruelty of this accounting is that none of it registers physically. Radiation does not announce itself. There is no pain, no warmth, no sensation at all. A crew member could be accumulating molecular damage at a medically significant rate and feel completely fine. The body gives no signal. The ledger is the only signal. You feel ordinary while something irreversible is being written into cellular structure. In rooms that look entirely safe, on a day with no emergency, nothing unusual, nothing to warn you. That is the hidden architecture of Martian life. Not the domes or the rovers or the geology expeditions. The quiet accounting. The depth of rock overhead. The weekly hours remaining. The spreadsheet ticking upward in the background of every ordinary day. And radiation is only one of the forces working against the body underground. The surface has been neutralized as a living space. But living underground on Mars creates its own set of pressures, and not all of them are physical. Dust comes with you. That is the thing no engineering protocol has fully solved. You can bury the habitat under 2 meters of regolith. You can build radiation-hardened walls and pressurize every corridor. You can seal the sleep sanctum until it reads like a hospital clean room. But every time a crew member comes in from the surface, dust comes with them. It clings to the suit. It clings to the gloves, the visor, the seams. And when the inner airlock door opens, some fraction of what was outside is now inside. That fraction never fully leaves. Martian dust is not like the dust in a house or the grit on a hiking trail. The average particle is roughly 3 micrometers in diameter. That is about 4% of the width of a single human hair. Particles that small do not settle quickly. They drift. During a regional storm, they can stay suspended for weeks. During a global storm, months. And the storms on Mars are not a seasonal inconvenience. They are a planetary event. A single storm can swallow the entire planet, cutting solar energy collection by more than 80%, for weeks at a stretch. But the threat is not what the numbers suggest. The wind that carries this dust sounds lethal when you first hear the numbers, 60 to 100 kilometers per hour. And you have already learned that Martian wind carries almost no physical force in the thin atmosphere. So, the wind itself is not the hazard. It is a delivery mechanism. What it delivers is the problem. The composition of Martian dust is a short list with catastrophic consequences. Silica, iron oxides, gypsum, and perchlorate salts. Silica alone is dangerous. Miners and industrial workers on Earth who inhale fine silica particles over years develop silicosis, an incurable respiratory disease that scars and stiffens lung tissue, progressively reducing the capacity to breathe. There is no treatment that reverses the scarring. There is only management of the decline. That hazard exists in Martian dust regardless of everything else in it. But the perchlorate content is the part that changes the scale of the problem entirely. Perchlorates are chlorine-oxygen compounds, toxic to humans even in small amounts. On Earth, perchlorate contamination in drinking water triggers regulatory intervention at concentrations of just parts per billion. That is the threshold at which authorities in the United States consider the water unfit to drink, parts per billion. Martian regolith carries perchlorate at 0.5 to 1% by weight, not parts per billion. 0.5% of every handful of Martian soil. Orders of magnitude past the level that makes Earth water unfit to drink. When perchlorate is inhaled rather than ingested, the route into the body is faster and more direct. The particles dissolve in the moist tissue of the lungs and enter the bloodstream without passing through the digestive system at all. No filtration step, no delay. Once in the blood, perchlorates interfere with iodine uptake in the thyroid gland, disrupting hormonal regulation. Chronic exposure produces thyroid dysfunction. At higher levels, the damage extends to bone marrow. The condition is called aplastic anemia, a failure of the marrow to produce the blood cells the body needs. It is not a distant theoretical outcome. It is a documented consequence of sustained perchlorate exposure, and the threshold for triggering it on Mars would be measured not in years, but in accumulated milligrams. A 2025 study in the journal GeoHealth from researchers at the University of Colorado, the University of Southern California, and partner institutions reviewed the full toxic profile of Martian dust and reached a specific conclusion. Long-term dust exposure is one of the most serious and underappreciated hazards of Mars habitation. Not the most dramatic hazard, Not the most acute one, the most underappreciated one, meaning the one most likely to be treated as a secondary concern until it is too late to treat. Part of why it is underappreciated is the particle size. 3 micrometer particles fall into a category called respirable dust. They are small enough to pass through the upper airway, through the bronchial passages, and down into the alveoli, the tiny sacs deep in the lungs where oxygen moves into the blood. The body's defense mechanisms, the small hairs and mucus that catch larger particles before they travel too far, are designed for bigger threats. They do not efficiently intercept particles this fine. The particles lodge in alveolar tissue. Over weeks and months, they trigger an inflammatory response. The tissue responds by scarring. That scarring is fibrosis, a permanent reduction in the lung's ability to exchange gas, not a temporary irritation, a permanent architectural change. And the dust carries something else: nanophase iron oxides, particles so small they exist at the boundary of chemistry and physics, giving Mars its red color and making the dust simultaneously magnetic and electrostatically charged. That charge is why the dust clings, not loosely, the way dirt sits on a boot. It bonds at a molecular level. Laboratory simulations confirm that standard cleaning techniques, brushing, blowing, vibration, do not remove it. The particles attach to fabrics, seals, visors, and skin, and stay attached. The same property that makes dust storms globally catastrophic makes individual particles personally inescapable. Apollo astronauts encountered a version of this with lunar dust. After short surface excursions, they returned to the lunar module to find dust coating every surface they had touched. It clogged mechanisms. It scratched visors. It irritated eyes and throats. Crews reported respiratory symptoms that persisted even after returning to the relatively clean environment of the capsule. Those were short missions, measured in hours of surface time. The lunar dust they dealt with was coarse compared to what Mars offers. Martian dust is finer than lunar dust. And unlike the Moon, Mars has an atmosphere that keeps its dust continuously mobile, continuously resuspended, continuously available for the next airlock cycle to bring inside. Every entry and exit is a contamination event. Every suit brought in carries trace amounts that filtration systems catch, but cannot eliminate entirely. Over months, the internal dust concentration in a habitat rises, slowly, but without stopping. On Earth, when a worker in a hazardous dust environment begins showing symptoms, the response is immediate and specific. Remove them from exposure, rest, monitoring, medical evaluation. The exposure ends. On Mars, there is nowhere to be removed to. The habitat is the exposure environment. The airlock cycles continue because they must. The suits go back on. The surface operations continue because without them, the mission ends. There is no clean room somewhere else on the planet to transfer to. The crew lives inside the problem, every day, for as long as the mission lasts. And on the days when a global storm arrives, the problem compounds. In the spring of 2018, a global dust storm began spreading across Mars. Within weeks, it had covered virtually the entire planet. NASA's Opportunity rover, which had been operating on the Martian surface for nearly 15 years, fell silent. The storm coated its solar panels with a layer of fine particles, thick enough to drop power generation below the threshold needed to keep the rover's systems alive. Opportunity never recovered. Opportunity was a machine. It had no need for breathable air, no water recycling to maintain, no heating system keeping tissue from freezing. It needed only electrical power. And the storm took that. A human crew facing the same storm would watch the power budget shrink in real time. Oxygen generation slows as electrolyzer power drops. Water recycling falters. Heating struggles. The crew is sealed inside, breathing recycled air, in a habitat losing energy to a storm they cannot stop and cannot step outside to address. The panels are coated with dust, bonded at the molecular level. Cleaning them is a surface EVA task, performed in suits that bring more dust back with them each time. And the storm is still running. The dust does not just threaten health over months and years, it threatens survival over weeks. Nuclear power changes the energy equation. Radioisotope thermoelectric generators, the devices that kept Curiosity and Perseverance running through storms, Eliminate solar dependence. Small fission reactors proposed for crewed missions would do the same, but they carry their own mass costs, shielding requirements, thermal management challenges, and failure modes. They solve the storm power problem while introducing a different category of engineering risk. Either way, the dust does not stop. The particles do not become less fine because a reactor is running. The percolorate does not become less toxic because the lights stay on. The airlock cycles continue, and the slow accumulation inside the habitat continues with them. The crew is sealed underground, shielded from radiation overhead, and sealed in with something that found its way through every door regardless. Dust, radiation, isolation, pressure management, power budgets. None of these problems are separate from each other. Each one pulls on the others, and the structure of that entanglement is where the real difficulty of Martian habitation lives. That entanglement is not a coincidence. It is the nature of the place. Step back from any single hazard, and a pattern emerges. Radiation forces the crew underground. Underground means confinement. Confinement means every system that produces breathable air, drinkable water, and livable temperature must run continuously inside a sealed space. The suits that allow the crew to move outside protect against vacuum and cold, but they carry dust back through every airlock cycle. The shielding that blocks radiation overhead traps that same dust inside. The filters that catch the dust run on power. The power systems that supply the filters are the same ones a global dust storm can cut by more than 80%. Pull on any one thread, and 3 others pull back. There is no Earth environment where this is true. That is the point. Antarctica comes closest to Mars in cold, and the comparison is worth making carefully. The Antarctic interior reaches temperatures that kill an unprotected person within minutes, but the air above that ice is breathable. Radiation there is low. A person in proper gear can inhale the environment rather than filter every molecule of it. A submarine takes confinement further than any Antarctic station, sealing a crew inside a hull for months with no horizon and no open sky. But the hull handles the pressure difference with engineering margins built for that single purpose, and the ocean outside contains no toxic suspended particles and no ionizing radiation stream to accumulate in tissue. A deep mine subjects workers to abrasive dust and close quarters for hours at a stretch. But at shift's end, the workers leave. They step into open air. The exposure ends because there is somewhere else to go. On Mars, there is no somewhere else. Every major hazard operates at full intensity, simultaneously, with no dimension of the environment where a human body can simply exist without active mechanical intervention, keeping it alive. Not one system running in the background while the person rests. Every system. Always. This shows up most visibly in equipment degradation, and the evidence is not theoretical. Every rover that has operated on the Martian surface has confirmed it. Dust works into mechanical joints, seals, and bearings. It coats optical sensors and lenses. It reduces thermal radiator efficiency over time. It finds its way into electrical connectors and creates short circuits in exposed wiring. Rovers have shown all of these failure modes in detail. And rovers do not breathe. They do not need sterile air or filtered water. They carry no tissue that reacts to a perchlorate particle lodged in a lung. They are machines, and dust still degrades them methodically. For human habitation, the requirements are an order of magnitude tighter. Pressure seals must resist not just the force differential between inside and outside, but the fine abrasive particles working into every gap over months of cycling. Airlocks must operate reliably, with particles jamming moving parts, thousands of times across a multi-year mission. Filters must capture particles down to 1 micrometer, the threshold at which Martian dust remains suspended and respirable, without clogging so quickly that the filtration system itself becomes a maintenance crisis. Ventilation ducts, heat exchangers, and humidity systems must function under conditions that would trigger automatic shutdown in any terrestrial cleanroom facility. And each of these requirements does not stand alone. Every additional requirement adds weight, complexity, potential failure modes, and maintenance hours. On a surface where resupply takes years and replacement parts cannot be ordered, every added system is another line in a ledger of things that can go wrong and cannot be quickly fixed. But the picture most people carry is different. None of this is what people imagine when they imagine the danger of Mars. The cinematic version of Mars danger is a storm rolling over the horizon, or a reactor alarm, or a breach in the hull. A single dramatic event with a clear cause and a race against time. That version has a protagonist and a crisis and a moment when everything changes. It maps onto stories humans already know how to tell. The real version does not look like that. No one will make a documentary about a crew tracking their cumulative millisievert count for the 8th consecutive month. No one will film a crew member replacing an airlock gasket for the 4th time in a season because dust has worked into the seal again. These are not climactic moments. They are slow, grinding, invisible burdens. They accumulate across ordinary days, not emergencies. And that is exactly what makes them dangerous. The gap between survival and failure on Mars does not widen and then narrow dramatically. It narrows continuously. It erodes in increments small enough to miss until the margin is thinner than the dust particle lodged in the airlock seal. This is a permanent emergency. Not a sequence of separable problems that a well-designed mission solves one by one, after which the crew lives in something resembling normalcy. A permanent emergency that never escalates into a single crisis, and never resolves into safety. The crew manages it daily, hourly, in systems they cannot see, against hazards they cannot feel, until they leave, or until something fails. And radiation and dust, as comprehensive as they are, represent only 2 entries on that list. Even with the shielding architecture working correctly, even with filtration keeping dust concentrations inside acceptable bounds, every molecule of oxygen the crew breathes must still be actively produced. Every drop of water must be recovered, treated, and recirculated. Every calorie must come from stores that arrived with the mission, or from food systems that require power and maintenance, and sufficient light to function. Every watt of power must be generated and distributed and protected from the same dust storms that threaten everything else. The body's requirements do not pause while the engineering problems are managed. They run in parallel with all of it, continuously, from the first day to the last. The exterior hazards close here. What remains is the interior architecture that makes survival possible at all. The systems that manufacture the conditions the human body requires, in an environment that produces none of them on its own. Start with the one thing Earth gives away for free, everywhere, without exception: air. In the Arctic, the cold is savage and the darkness in winter lasts for months, but the air above the ice is breathable. On a submarine running deep, the crew is sealed inside a pressurized metal cylinder, with no access to the surface. But the reactor running the vessel produces effectively unlimited power. In the Sahara, water hides in the deep aquifers below the sand, and the sun provides warmth and energy around the clock. Even at the summit of Everest, at the edge of human survivability, the pressure is high enough to keep blood liquid in the veins, and the gravity is the gravity the human skeleton spent a lifetime building itself for. Every extreme environment on Earth gives humans at least one thing for free. Mars gives nothing. Not one thing. The air is not breathable and cannot be made breathable by filtering it. Water is not flowing anywhere accessible. The soil is toxic. Sunlight arrives weakened and intermittent, offering no warmth because there is no thermal atmosphere to trap it. Temperature and pressure are both independently lethal. The human body, which requires breathable air and liquid water and food, and regulated temperature and a stable pressure environment, arrives on Mars at a place that provides none of those things, passively, ever. Every single requirement of human biology must be manufactured, recycled, monitored, and maintained. All of them, simultaneously, without interruption, for as long as anyone remains on the surface. This is the difference between Mars and every other dangerous place humans have ever operated. The ISS is complex. Life support on the ISS is sophisticated and demanding, but the ISS exists within rescue range of Earth. Resupply missions arrive every few weeks. Spare parts can be launched on short notice once a problem is identified. Ground teams follow every system in real time. And if something goes wrong badly enough, a Soyuz or Crew Dragon can have the crew back on Earth's surface within hours. None of that is true on Mars. A cargo flight from Earth takes 6 to 9 months to arrive. Launch windows open only every 26 months, when the orbits of Earth and Mars align favorably enough to make the crossing practical. If a critical component fails 3 months after the last window closes, the wait for a replacement is roughly 2 years, assuming the part was identified, manufactured, loaded aboard a rocket, launched on schedule, and landed successfully. The ISS operates inside a safety net. Mars does not have one. So consider what that means for something as fundamental as the air itself. The Martian atmosphere is 96% carbon dioxide. Oxygen exists at 0.16%. That is not a thin concentration of oxygen that could be enriched by some kind of filtration system. Filtering implies separating something that is already there in meaningful quantity. At 0.16%, there is almost nothing to separate. The molecular bonds must be broken, oxygen must be made, not gathered. Two approaches are well understood. Water electrolysis splits water molecules into hydrogen and oxygen using electricity. It is proven technology, used on submarines and on the ISS for decades. CO2 electrolysis splits carbon dioxide into carbon monoxide and oxygen using electricity. It works directly on the Martian atmosphere, which is why NASA flew a device called MOXIE aboard the Perseverance rover to test it. MOXIE worked. During its test cycles on the Martian surface, it produced oxygen at roughly 6 grams per hour. Here is where the math becomes the point. A resting adult consumes approximately 840 grams of oxygen per day. That is about 35 grams per hour. One MOXIE unit, running continuously, covers roughly 17% of one person's needs. Not one person's needs for the crew. One person. A crew of 4 needs at least 140 grams per hour, every hour, with 0 downtime. That is more than 23 times what a single MOXIE demonstrated. Scaling is theoretically feasible, but every time you scale a system like this, you multiply the power it demands, the heat it generates, the mass that had to be launched and landed, the plumbing connecting the components, and the number of points where failure is possible. Running continuously means no scheduled maintenance windows. If oxygen generation stops, the timeline is not forgiving. After 8 hours in a sealed habitat, atmospheric oxygen levels begin to drop noticeably. After 24 hours, with 4 people consuming and CO2 accumulating, concentrations reach the threshold for cognitive impairment. After 48 hours, the situation is a medical emergency. That is not a background utility problem. That is the foreground of existence, measured in hours. CO2 removal runs in parallel and faces the same constraints. 4 people exhale approximately 4 kilograms of carbon dioxide every day inside a sealed volume with no natural ventilation. CO2 above 1% causes headaches and impaired cognition. Above 5%, it becomes acutely dangerous. Scrubbing systems using chemical absorbents or regenerative processes must run continuously alongside oxygen generation, drawing on the same power supply, adding their own failure modes. And the failure mode itself is cruel. The first symptom of scrubber failure is impaired judgment. The person least likely to recognize that symptom is the person experiencing it. A scrubber problem does not announce itself with an alarm you can feel. It announces itself as slightly poor decisions from people who believe they are thinking clearly. The atmosphere inside the habitat is not a passive medium. It is a managed industrial gas mixture, maintained continuously by machines. Humidity adds its own demands. 4 bodies exhaling, perspiring, cooking, and maintaining basic hygiene in a sealed volume produce moisture continuously. That moisture, if not extracted, promotes microbial growth on surfaces, corrodes electronics, fogs optical sensors, and creates conditions for fungal contamination in food production areas. Dehumidification must run continuously, and every litre captured feeds back into the water loop, because water on Mars is not simply available. An adult needs roughly 2.5 to 3 litres of drinking water per day at moderate activity. Add food preparation, hygiene, medical use, and crop irrigation, and the per-person demand climbs significantly. The ISS recycles approximately 90% of its water, capturing moisture from the air, processing urine, and reclaiming wastewater. A Mars habitat must match or exceed that efficiency, because the alternative sources are difficult. The most viable new source of water on Mars is subsurface ice, buried under centimeters to meters of regolith at higher latitudes and some mid-latitude regions. Extracting it requires excavating in extreme cold, melting it, and then filtering it to remove perchlorate salts, the same compounds that make Martian soil toxic. Hydrated minerals are an alternative but yield less water per unit of energy spent. Atmospheric water vapor, the third option, totals only 10 to 20 precipitable micrometers across the entire Martian sky. That is nearly negligible. The atmosphere that is 96% carbon dioxide holds almost no water at all. And here is a coupling most people do not think about. Every litre of water split for oxygen production via electrolysis is a litre not available for drinking, washing, or growing food. The two most essential resources on Mars compete for exactly the same feedstock. The allocation between them shifts constantly with crew activity levels, crop cycles, atmospheric leakage rates, and recycler efficiency. It is a daily calculation with no comfortable margin. Food sits underneath all of it. One person requires roughly 2,000 calories to 2,500 calories per day. For a crew of 4 over a 2-year surface stay, that is 3 to 4 metric tons of food. Shipping that mass from Earth is prohibitive for anything beyond short-duration missions. For permanent settlement, growing food locally is not an option that would be nice to have. It is an absolute requirement. Growing food on Mars means pressurized, artificially lit, climate-controlled modules inside the habitat, almost certainly using hydroponic or aeroponic systems where plants grow in nutrient solutions rather than soil. Martian regolith cannot be used as agricultural soil in its native state. The perchlorate content alone would make anything grown in it toxic. The regolith also lacks organic matter, microbial communities, and the nutrient profile crops require. Before any plant could grow in it, it would need extensive washing to remove perchlorates and toxic salts, supplementation with nitrogen and phosphorus fertilizers, and inoculation with microbial cultures from Earth. Even then, crop selection is severely constrained. The plants that work on Mars are high-calorie, fast-growing, and space-efficient. Potatoes, soybeans, wheat, rice, lettuce, a limited range of vegetables. Dietary variety is minimal, which matters not only nutritionally but psychologically, over months and years. Animal protein is nearly impossible at scale. Even small livestock like chickens or fish demand prohibitive feed, water, atmospheric load, waste management, and space relative to the calories they produce compared to plants. A Mars settlement would almost certainly be vegetarian by necessity, not choice, and crop failure on Mars carries stakes that have no Earth equivalent. On Earth, a failed harvest means imports from somewhere else. On Mars, there is no somewhere else. A contamination event in a hydroponic bay, a lighting failure, a nutrient miscalculation, a disease moving through the only food source, any of these can erase weeks or months of production. Backup reserves are finite. Watching the supply total decline with no way to replenish it is a category of pressure most humans have never experienced. Waste connects back to everything else. 4 people produce continuous biological and material waste. Urine feeds into the water recycling loop. Solid waste must be dried, sterilized, and either stored or composted for agricultural use. Because in a sealed habitat, biological waste is both a health hazard and a resource. Food scraps, plant trimmings from hydroponics, worn filters, contaminated material, packaging, broken components, all of it must go somewhere. There is no landfill, no garbage truck, no sewer. An overlooked failure in waste processing can introduce pathogens into the water supply, contaminate the food systems, or generate toxic gases in the shared atmosphere. On Earth, sanitation is invisible infrastructure. On Mars, it is a daily hands-on operation the crew cannot delegate to anyone. Power underlies every system described: oxygen generation, water extraction and recycling, food production, lighting, heating, air circulation, dust filtration, communications, computing, robotics, suit charging, airlocks. Every instrument and every tool runs on electricity. Without continuous, reliable power, the other systems fail in sequence, and the sequence is not slow. Mars receives approximately 43% of the solar energy per unit area that Earth receives. On a clear Martian day with no storms, solar panels work, but they produce power for only about half of each day. Nighttime requires stored energy, and dust storms, which can reduce solar irradiance by more than 80% for weeks at a stretch, arrive precisely when heating demands are highest. A 4-person habitat must maintain an interior temperature of roughly 20 to 22 degrees Celsius against an average exterior of around minus 60 degrees. That is an 80-degree differential bleeding heat through every square meter of exterior surface into frozen ground below and near vacuum above, continuously, every hour of every Martian night. The total power budget for a 4-person habitat, accounting for life support, food production, heating, and basic operations, runs to roughly 40 to 100 kilowatts of continuous generation. A typical American home uses an average of about 1.2 kilowatts. A Mars habitat requires the continuous output of 30 to 80 of those homes, in a location where the sun provides less than half the energy it provides on Earth, and goes away entirely at night. NASA's Kilopower project demonstrated a small fission reactor concept, producing 1 to 10 kilowatts continuously, independent of dust, darkness, or season. Scaling that technology to 40 or 100 kilowatts is active research, not a finished product. Reactors add mass, require shielding, generate waste heat that must be managed, and introduce a failure mode where a power loss arrives, alongside a potential radiological contamination event, in a sealed habitat with no evacuation option. The likely architecture is solar arrays combined with battery storage combined with nuclear redundancy. Each layer costs mass, volume, maintenance attention, and complexity. Each layer adds its own failure modes to the list the crew manages. And all of it, the power systems, the oxygen systems, the water loops, the food modules, the waste processing, the atmospheric management, runs simultaneously, every day, with no pause and no assistance arriving for years. The body's requirements do not negotiate with the engineering. They simply continue. And somewhere underneath all of that, there is the original purpose that brought the crew to Mars in the first place. Imagine waking up inside all of that. Not waking up to it, not beside it, not after someone else has already checked on it. Waking up inside it, responsible for every part of it, before your eyes have fully adjusted to the light. The light itself is artificial. It is tuned to simulate dawn, cycling through a spectrum chosen to ease the human nervous system into consciousness. No window will ever show you a Martian sunrise from here. You are sleeping under a meter of regolith, and the sun, when it rises over the crater rim 40 meters above you, reaches you only as a number on a panel. You check the panel before you eat. The atmospheric monitor reads first: oxygen concentration, CO2 level, humidity, pressure, trace contaminants. This morning, Module 2's CO2 scrubber is drawing 3% above its normal power load. That means either a degrading absorbent bed approaching saturation or a fan bearing starting to fail. You log it. You move to the water dashboard. Throughput, purity, filter pressure drop. One filter is approaching its replacement threshold. You log that too. Then the hydroponic module, pH, reservoir temperature, light cycle. 2 potato plants are showing early calcium deficiency in the leaf margins. You adjust the nutrient mix. Then the battery charge state and solar array output. Yesterday's dust-reduced panel efficiency by 4%. Someone will need to clean the arrays today, adding a task that requires a suit, an airlock cycle, and at least 90 minutes. Then the radiation log. Cumulative crew dose for the week is still within budget. All of that before breakfast. Breakfast is rehydrated grain porridge and a small serving of greenhouse lettuce. The same as yesterday, the same as the day before. Crop variety comes only in slow, staggered rotations across a growing calendar planned months in advance. This is a normal morning on Mars. A bad morning is when 2 of those readings come up red instead of yellow, and you stand there for a moment deciding which emergency comes first. Think about what that word means. On Earth, invisible infrastructure carries almost all of it. A grid delivers power before you wake. Treatment plants have already cleaned the water you will drink. Supply chains have already stocked the food you will eat. The atmosphere has already filled your lungs while you slept without asking anything of you. When something in that web fails, a specialist arrives within hours carrying parts from a global manufacturing network. The support is so embedded in the background of ordinary life that most people mistake it for reality itself. It is not reality. It is an apparatus. You have simply never been responsible for maintaining it. On Mars, every part of that apparatus is inside the habitat walls, and the crew is the specialist. Every pump, every valve, every filter, every sensor, every seal, every circuit board, every motor, every gasket. Understanding them, monitoring them, diagnosing them, repairing them. That is the job. Not occasionally, not when something breaks. Every morning, before the meal. But the scale is worse than that. ISS studies already show that maintenance and housekeeping consume 40 to 50% of available work hours aboard the station, and the ISS exists in low Earth orbit, with resupply every few weeks, engineering teams available by radio in real time, and an evacuation vehicle docked to the hull. On Mars, the percentage would run higher, more systems, a harsher environment grinding through seals and bearings faster than any laboratory test predicted. Scarcer parts, worse consequences for anything deferred. A Mars crew would not be explorers who occasionally fix things. They would be maintenance technicians who occasionally explore. The inventory problem compounds everything. Every spare part either ships from Earth at enormous cost or gets fabricated locally using early-stage in-situ resource utilization, the process of making usable materials from what Mars itself provides. Some parts can be 3D printed from regolith and recycled stock, structural brackets, simple casings, certain non-critical fittings, but pressure vessel seals, electronic circuit boards, precision sensors, medical equipment, these cannot be made from raw dirt and recycled plastic. Not with any technology that will exist on Mars in the near term. They must be anticipated, packed, launched, and landed intact, months or years before they are needed, based on failure predictions that may not match actual conditions on the ground. If a component fails unexpectedly, if a spare lands damaged, or if an earlier repair already consumed the only one available, the gap cannot be closed for years. The next launch window opens in 26 months. The cargo transit takes 6 to 9 months, and a replacement lands when it lands. Improvisation becomes a daily survival requirement, not a celebrated exception, a baseline condition. Apollo 13's CO2 filter fix, the Hubble mirror repair, the rover team workarounds that kept Opportunity moving long past its design life. Those moments entered history precisely because they were exceptional. On Mars, they would be routine, not the story a mission tells about itself in retrospect. The texture of every week. Communication compounds it further. An unfamiliar failure on the ISS gets expert guidance within seconds. Houston is watching the telemetry in real time, and a specialist who has spent a career on that specific system can walk the crew through a diagnosis while the crew is still holding the tools. On Mars, with a 4 to 24 minute one-way signal delay, a single exchange of question and answer consumes nearly an hour of mission time. A complex troubleshooting session stretches across a full day. Real-time collaboration becomes impossible. Every crew member must carry the depth and breadth of a plumber, an electrician, a mechanic, a chemist, a botanist, a medic, and a systems engineer, all at once, all the time, and diagnose under pressure without a second voice in their ear. Consider what a plausible Tuesday might actually look like. A dust storm cuts solar output by 60%. Battery reserves deplete faster than the drawdown plan assumed. The crew begins shedding non-essential load, but heating, air circulation, and oxygen generation are not non-essential. Water recycling can pause for a day or two before the contamination risk becomes acute. Crop lighting can be reduced, but not eliminated without destroying weeks of food mid-cycle. Rationing begins, reserves continue falling. Then a water recycling pump seal, stressed over months by perchlorate mineral deposits from the filtered water passing through it, starts to leak. Now the crew divides attention between power management and water repair, simultaneously, using a finite parts inventory, while every hour of reduced air filtration slowly raises the dust concentration in the breathing air. The CO2 scrubber that was running 3% high this morning has not been investigated yet. It is still running 3% high. This is not a disaster movie. None of it is dramatic. A seal degrades. A sensor drifts from calibration. A filter clogs 2 weeks ahead of its projected replacement date. A battery cell underperforms at low temperature. A crop rack develops a fungal infection in the high humidity near the irrigation lines. None of it alone is fatal. Together they consume every available hour in reactive maintenance, leaving nothing for the geology transect that was planned for Tuesday afternoon or the atmospheric sampling run that was scheduled for Wednesday. Mars does not attack with a single catastrophic event. It erodes margins through dozens of small, simultaneous stresses. The gap between the crew and the limit does not open and then close dramatically. It narrows, slowly, in increments small enough to miss individually, until the margin is thinner than the dust particle lodged in the airlock seal. What this strips down to, at the end of a day like that Tuesday, is something worth sitting with. Living on Mars is not living near a machine or living with the help of one. It is living inside one. The machine is your atmosphere, your water, your food, your warmth, the barrier between your bloodstream and the vacuum waiting on the other side of every wall. You are the machine's mechanic, operator, monitor, and most vulnerable component. If you are also the person the machine depends on to keep it running, and also the person who will die first if it stops, the position is unlike anything our species has occupied before. The engineering is extraordinary, among the most remarkable things we have ever attempted, and that statement is not hyperbole. But the engineering does not change the fundamental equation. On Mars, human life is not sustained by an environment, it is sustained by an apparatus. And the apparatus is always, without pause, approaching the next small failure. The science that brought the crew there in the first place is still waiting. But there is one problem the science cannot reach. Not the air, not the water, not the dust, not the radiation. Those are engineering problems. Difficult ones. Staggering ones. But they are, at least in principle, solvable. You can manufacture air. You can recycle water. You can bury a habitat under 2 meters of regolith and block most of the radiation trying to reach the people inside. What you cannot do is increase a planet's gravitational pull. Mars exerts roughly 0.38 g, 38% of Earth's surface gravity, and every structure in the human body that evolved under Earth gravity, every bone, every muscle, every vessel, every fluid distribution pattern, exists on Mars in a mechanical environment it was never built for. You cannot engineer around that. Not inside a surface habitat. Not at any budget. Here is what makes this uniquely difficult. Most of the hazards covered so far have at least some data behind them. Radiation doses measured. Filter specifications tested. Pressure seal failure modes documented across thousands of cycles. But with partial gravity, the long-term human data is almost entirely absent. What we have instead is the microgravity baseline from the International Space Station, and a handful of newer fragments that are only beginning to suggest what 0.38 g might actually do. The microgravity data is sobering enough on its own. Astronauts aboard the ISS lose roughly 1 to 2% of bone mineral density per month in weight-bearing bones, the hip and the spine. They exercise approximately 2 hours a day, every day, specifically to slow that loss. The loss continues anyway. Muscle mass declines, particularly in the legs and lower back, the muscles most dependent on load-bearing in Earth gravity. The cardiovascular system deconditions as the heart adapts to pumping blood without gravity pulling fluid away from the chest. Fluids shift headward, raising pressure inside the skull, and this can trigger a condition called spaceflight-associated neuroocular syndrome, a syndrome in which elevated intracranial pressure compresses or reshapes the optic nerve and damages vision. Immune function appears altered. Wound healing may be impaired. These are not rare complications. They are the documented baseline of human physiology in zero gravity, observed across dozens of long-duration missions. Mars is not zero gravity, it is 38% of Earth gravity. And for a long time, the assumption was that this would provide meaningful protection, 38% of the problem. But the picture did not hold. In 2022, a simulated partial gravity study examined osteoblast function, the cellular process responsible for building bone. What researchers found was a threshold effect. Bone-forming cell activity was substantially impaired at simulated Mars gravity. Not dramatically worse at lunar gravity, not dramatically worse at near microgravity. Already substantially impaired at 0.38 g. The protective gradient was not proportional. Mars gravity does not give humans 38% of the protection they would have on Earth. It may give them far less than that. Bone loss would be slower than in microgravity, but ongoing, month after month, year after year, with no mechanism to halt it. Then, in 2026, a team from the University of Rhode Island, Harvard Medical School, and international partners used an onboard centrifuge on the ISS to expose mice to varying gravity levels, including one close to Martian gravity at 0.33 g. The group held at 0.33 g showed partial mitigation of spaceflight-induced muscle atrophy compared to full microgravity. That sounds like progress, but full prevention of muscle loss only appeared at 0.67 g, roughly 2/3 of Earth gravity. Mars, at 0.38 g, sits below that threshold. The implication is uncomfortable. Mars gravity may slow muscle loss. It is unlikely to stop it. The consequences compound. Bone is not only structural, it is a mineral reservoir, and it houses marrow, which produces red blood cells, white blood cells, and platelets. Significant bone loss means hematological consequences. Reduced oxygen carrying capacity, weakened immunity. This is the same immune system already challenged by radiation. The same immune system operating with no infectious disease specialist on call. No hospital within 3 years of travel time. One vulnerability does not sit beside another. They feed each other. The cardiovascular unknowns add another layer. At 0.38 g, the heart works against some gravity, far less than it would on Earth. Whether years of that reduced workload produce clinically meaningful deconditioning is simply unknown. No human being has ever lived in partial gravity for more than a few days. The Apollo lunar surface missions, the only partial gravity human exposure in history, lasted days. Not months, not years, days. We have no data. We do not fully understand what a heart and a circulatory system become after a decade at 0.38 g. Whether fluid shifts toward the head occur at a clinically significant level in partial gravity is similarly uncertain. Even a partial and sustained elevation of intracranial pressure over years could contribute to progressive visual impairment. There is no ophthalmologist on call. All of this applies to adult settlers arriving from Earth. It gets deeper when you consider what happens when the settlement produces children. No mammal has ever been conceived, gestated, born, or raised in partial gravity. We do not know whether a fetal skeleton would develop adequate density at 0.38 g. We do not know whether fetal circulatory patterns would form correctly, given that circulation depends in part on the mechanical pressures imposed by gravity in a developing body. We do not know whether neurological development would proceed normally. The vestibular system, the inner ear's gravity-sensing apparatus, provides continuous input to the developing brain. Gravity is not background noise to a developing nervous system. It is signal. Alter it and the developmental consequences are unknown. And then there is the question that should stop the conversation for a moment. Could a child raised on Mars ever safely visit Earth? On Earth, the gravitational force on their body would be approximately 2.6 times what they had known their entire life. A skeleton that developed at 0.38 g, a cardiovascular system calibrated to 0.38 g, a vestibular system trained from birth to interpret 0.38 g. What would 2.6 times that load mean? We do not know, but the plausible answer is that a Mars-born child might be physiologically confined to Mars. Not by a technical limit, not by a launch window, by their own body. This is not distant speculation. If humans go to Mars to stay, reproduction becomes unavoidable within a generation, and we would be running the experiment in real time, on actual children, with no control group, no way to intervene if neurological development goes wrong, no way to move them to Earth gravity if the results are dangerous. The ethical weight of that is largely absent from popular conversations about Mars colonization. It should not be. Even for healthy adult settlers, the trajectory is one way by a mechanism that has nothing to do with fuel. Over 3 years, 5 years, 10 years of living at 0.38 G, the body adapts. Bones thin to the density the environment demands. Muscles find their new equilibrium. The cardiovascular system recalibrates to lower workload. At some point, the body is no longer an Earth body. It is a Mars body, shaped by reduced gravity in ways that may be partially, but not fully reversible. Returning to Earth would mean subjecting that Mars body to 2.6 times its accustomed gravitational load. Re-entry and landing forces could injure weakened bones. Standing upright under full Earth gravity could cause syncope from a cardiovascular system adapted to far lower demands. Walking could produce stress fractures. Mars settlement may be biologically one way long before it becomes one way by logistics. The threshold is quiet. It does not announce itself. It is crossed somewhere in the middle of an ordinary year, and by the time anyone recognizes it, the adaptation is already done. Gravity is not the only thing shaping that adaptation. The body has been the subject for 10 sections now. Set it aside for a moment, because there is another dimension to this that most projections underweight, and in some ways it may be harder to solve than bone density or radiation exposure. The mind. What happens to human psychology inside a sealed metal enclosure on a planet with no breathable air, no natural light, no immediate community beyond the 4 or 5 people sharing that enclosure, and no possibility of leaving it for the rest of your life? We have some data. Not much, but some. In July 2024, NASA completed the first mission of its Shapir program. 4 volunteers spent 378 days inside a simulated Mars habitat at Johnson Space Center in Houston. The habitat was roughly 1,700 square feet. Communications were artificially delayed by up to 22 minutes each way, mimicking the actual signal travel time between Earth and Mars. The crew conducted simulated EVAs, managed simulated equipment failures, followed restricted resource protocols. By the standards of Mars analog studies, it was thorough. When the crew emerged, they described what they had missed. Green grass, blue sky, fresh air on their faces. Those sound like small things. They are not small things. The human brain did not develop in sealed metal enclosures. It developed over hundreds of thousands of years in open landscapes with variable light, shifting wind, biological diversity, distant horizons, the irregular sounds of a living world. Environmental psychology has documented this in detail. Access to nature, even through a window, measurably reduces cortisol levels, improves concentration, and supports emotional regulation. Confinement in small, monotonous, artificially lit spaces produces the measurable opposite: elevated stress hormones, disrupted sleep, impaired concentration, progressive emotional flatness. There is even a named pattern for it: the third quarter phenomenon, a documented decline in morale and performance that typically arrives about 3/4 of the way through a long, isolated mission. Crews hit a wall, focus narrows, motivation drops, minor conflicts grow heavier. On any analog mission, the third quarter phenomenon eventually resolves, because the mission ends. On Mars, there is no end date. The third quarter arrives, and there is no fourth quarter to wait for. But here's where it gets strange. Every analog mission, including Shapir, retains a psychological safety net so fundamental that the crews often do not consciously register it. They know they will leave. Earth is out there, with all its sensory richness, waiting. That knowledge shapes every hour inside the habitat in ways that are difficult to quantify, but impossible to overstate. It moderates the anxiety. It puts a frame around the confinement. It makes the walls survivable because the walls are temporary. On Mars, the safety net does not exist. No walking outside without a full pressure suit. No fresh air, ever. No blue sky, ever. No green landscape, ever. The sensory deprivation is not a phase. It is the permanent condition of existence. The light compounds this in ways that are easy to underestimate. A habitat buried under 1 to 2 meters of regolith has no natural sunlight reaching the interior. No sunrise warming the ceiling. No shift from the bright blue of midday to the amber of early evening. Interior lighting is artificial and is typically engineered to support crop photosynthesis, meaning the spectrum it produces is measurably different from the full spectrum light the human brain uses to regulate its sleep-wake cycle. Submarine crews, Antarctic winter-over teams, and shift workers in facilities without windows all show the same pattern under depleted natural light cues: fragmented sleep, daytime fatigue, suppressed immune function, mood disorders that deepen with duration. Dedicated circadian lighting systems could help, but a simulated sunrise in a sealed underground room is not the same stimulus as actual sky. The brain knows the difference. Not consciously, necessarily, but the brain knows. The Mars 500 study produced some of the clearest physiological evidence of what happens when you push isolation further. In Moscow, from 2010 to 2011, 6 crew members spent 520 days inside a facility designed to replicate a Mars transit and surface mission. Researchers measured stress biomarkers at regular intervals, cortisol levels, serotonin metabolites, dopamine concentrations. The disruption was documented not just in self-reported mood data, but in blood and urine chemistry. Disrupted sleep-wake cycles, reduced physical activity, measurable hormonal shifts. One crew member experienced a persistent depressive episode that lasted for months. Another became progressively withdrawn. Interpersonal conflicts emerged and were managed through deliberate social protocols, but the strain showed up in the data whether the crew discussed it or not. The Mars 500 study lasted 520 days. Mars settlement means decades. Think about what that means. The same walls, the same faces, not for a year and a half, but for the rest of your life. The person you clashed with over breakfast is the person you eat dinner with tonight, and tomorrow night, and every night after that. Because there are only 3 or 4 or 6 other humans within roughly 100 million kilometers. Social friction that on Earth resolves easily, because you can walk away, visit a friend, change your environment, simply step outside becomes inescapable when every door leads to another room in the same machine. That creates a problem no analog program has adequately addressed. The question of authority. Who decides how to ration power during a dust storm? Who decides which failing system gets repaired first when 2 fail at the same time? Who decides whether a crew member in a depressive episode should be relieved of critical duties? And who absorbs those duties in a crew of 4 that is already at full capacity? On the ISS, Mission Control in Houston or Moscow holds operational authority. Disagreements between crew members can be mediated by ground teams. The structure of command runs through institutions on Earth. On Mars, with a one-way communication delay of 4 to 24 minutes, real-time mediation is physically impossible. A single back-and-forth exchange about an acute conflict takes the better part of an hour. The crew must govern itself. It would be the most isolated self-governing community in human history, making life and death decisions by consensus or command, with no court, no ombudsman, no option to transfer out, no recourse if the process breaks down. No analog mission has tested governance under those conditions, not even close. And then there is the distance itself. Not just the physical distance, but what the communication delay does to human connection over time. A conversation with a family member on Earth would mean recording a message, sending it, and waiting 8 to 48 minutes for a reply. Real-time dialogue cannot exist. Video calls as we know them cannot exist. Every exchange with a partner, a parent, a child becomes an exchange of recorded messages, with the emotional cadence of letters rather than conversation. There is a phrase that appeared in the psychological literature on isolated crew communication that is worth sitting with. Over time, the delay transforms communication from a lifeline into a reminder of distance. Months pass, then years. Earth becomes abstract. The people on it become increasingly disconnected from the lived texture of life inside the habitat. They do not share the smells, the sounds, the small daily frictions and routines. Settlers develop their own social norms, their own interior culture, shaped entirely by the conditions of the enclosure. The research on isolated communities, Antarctic research stations, submarine crews, remote military outposts consistently documents the same pattern: social drift. The isolated group progressively identifies less with the home culture and more with the immediate community of shared experience. The people left behind become, in the most literal possible sense, voices from another world. On Earth, social drift is a temporary phase. The mission ends. The submarine surfaces. The Antarctic crew flies home. On Mars, social drift is permanent and deepening. Depression becomes, under these conditions, not a risk, a near certainty, for some crew members over multi-year durations. Not personal failure, not weakness, a predictable neurobiological response to chronic confinement, sensory deprivation, social limitation, and the absence of environmental novelty. The brain requires a threshold of new sensory input to maintain normal emotional regulation. Below that threshold, dopaminergic and serotonergic systems, the brain's machinery for motivation, pleasure, and emotional responsiveness, downregulate. The symptoms overlap with clinical depression, loss of motivation, emotional numbness, difficulty concentrating, disrupted sleep, social withdrawal. On Earth, depression is treated with therapy, medication, and environmental change. Environmental change is the first-line response. Remove the person from the stressor, alter their surroundings, give the brain new inputs. On Mars, that option is unavailable, not temporarily, by definition. The environment cannot be changed because the environment is the habitat, and the habitat is the only place that exists. Medication supplies are finite and cannot be easily resupplied. Therapy from Earth-based psychologists is conducted through time-delayed messages. The crew manages its own psychological health using the coping resources it brought inside an environment that systematically erodes those resources, with no external intervention possible in real time. The body faces hazards that compound across months and years. The mind faces a different kind of compounding, one that does not announce itself in sensor readings or instrument alerts, one that moves slowly through the neural architecture, reshaping the capacity for resilience at exactly the moment when resilience is most needed. The physiology was always one half of the challenge. The psychology is the half that receives fewer headlines. It should not stay that way. Add one more limit to all the others, and the picture that emerges is not partial. It is complete. The Habitat Medical Bay holds a finite supply of pharmaceuticals, basic surgical tools, some diagnostic equipment, perhaps a compact imaging system. No operating theatre, no blood bank, no pharmacy with a full formulary. The crew medical officer is a broadly trained physician, skilled, prepared, but unable to perform complex surgery, manage rare conditions, or treat advanced disease. Not a specialist. A generalist holding the entire medical system together alone. A dental abscess can be managed with what is on hand. A kidney stone, an appendicitis, a fracture from a fall. These are hard, but they fall inside the margins of what one physician with limited tools can handle. But here is where the margin disappears. A ruptured appendix, a severe traumatic injury, an aggressive cancer. These require capabilities that do not fit in a cabinet. There is no evacuation on short notice. Under the best orbital alignment, a return to Earth takes months. Under the worst, it is impossible. The math is brutal and clear. A condition any emergency room on Earth could treat in an afternoon becomes a death sentence on Mars. Not a risk, not a possibility, a likely outcome with no intervention available. This knowledge does not stay in the background. It seeps into everything. Climbing a ladder to fix a ventilation unit is not just maintenance. A fall could fracture a bone that cannot be properly set. A bone slowly losing mineral density in 0.38 G in a body already borrowing from its own structural reserves. Eating from the hydroponic bay is not just a meal. It is an act of trust in a food supply where contamination could introduce pathogens. The limited antibiotic stores might not defeat. The faint existential weight of this never fully lifts. It is not paralyzing, but it colors every routine activity with a knowledge most people on Earth carry only abstractly, if at all, that the body is fragile, that fragile things break, and this body is already changing. A body undergoing chronic bone loss is a body that feels wrong, getting winded too easily, unstable on the feet, new joint pain on a day with no obvious injury. These are not dramatic symptoms. They accumulate, and they feed back. The mirror becomes an adversary. The daily exercise regimen, already consuming 2 hours of every day, becomes tinged with anxiety about whether it is working, whether the losses are being slowed or only postponed. Physical decline and psychological decline reinforce each other in a loop that has been documented in aging populations and long-term hospitalized patients on Earth. But it has never been studied in permanent off-world habitation. No dataset exists. The crew is inside an experiment that has no control group and no exit protocol. This is what separates Mars from every other extreme environment humans have occupied. Antarctic researchers rotate home after a season. Submarine crews surface after a deployment. ISS astronauts return to Earth after roughly 6 months. In every case, the hardship is endurable because it is temporary. Earth waits at the end of it. Earth with its gravity, its open skies, its food grown in soil under actual sunlight, its hospitals, its noise, its millions of strangers. The body and the mind know this. The knowledge that the stressor will end is itself a resource. It moderates anxiety. It makes the confinement survivable. Mars removes that resource entirely. The hardship is not the passage. The hardship is the destination. The confinement is not a phase. It is the life. The biological decline is not a temporary side effect. It is the trajectory. And the planet outside offers nothing. Not comfort, not restoration, not relief. The same silent hostility it has maintained for 4 billion years. Here is what the word living actually contains when you say it in the context of Earth. Breathing without thinking, drinking water from a tap, walking outside and feeling sun on skin without calculating the dose, eating food that grew in soil under open sky, hearing rain, standing in wind, sharing a city with millions of strangers, any of whom you might encounter tomorrow, knowing a hospital exists if you are sick, that a friend is a call away if you are lonely, that the world is vast with unseen places if you are bored. Earth life is embedded in a web of biological, social, and environmental support so integrated that we perceive it not as support at all. We perceive it as reality, as the normal texture of existing. On Mars, none of it is present. Air manufactured, water recycled from waste, food grown under artificial light in a closet-sized module, sky a rust haze through a small viewport, or not seen at all, social contact limited to the same 4 or 5 faces, year after year, with no other human within roughly 100 million kilometers, medical care fitting in a cabinet, exercise a treadmill in a corner, entertainment whatever digital files you brought, eventually exhausted. The sensory world shrinks to habitat dimensions. The emotional world shrinks with it. The word frontier does not fit. A frontier implies open space, new territory, the possibility of expansion. The daily inhabitant of a Mars habitat is not expanding into anything. The daily inhabitant is sealed inside a pressure vessel, maintaining the systems that keep the pressure vessel functioning, eating food grown inside it, breathing air recycled inside it, sleeping inside it, while outside, a planet of incomprehensible hostility waits with the patience of geological time. The frontier everyone pictures when they picture Mars is not out there on the rust-colored plains. The frontier is the 6 inches of engineered wall between your bloodstream and the vacuum. And still, some people will go. The impulse that drives our species toward hostile frontiers is not rational in the narrow sense. It does not need to be. Humans crossed oceans in wooden ships that killed half their passengers. They climbed mountains that offered nothing at the summit but wind and a view. They descended into caves, sailed into storms, walked into deserts, and launched themselves into orbit on pillars of controlled explosion. Not because these things were safe, because something in the human animal needs to know what is on the other side. Mars is on the other side. It is the next place. Some people will go fully aware of what awaits, but they should go with honesty, with the clearest possible understanding that what they are choosing is not a new life on a new world, not in any sense those words have previously meant. The images of Martian sunsets and open red landscapes are postcards from a world that will never welcome them. Daily existence will resemble operating a submarine more than homesteading on a prairie. Their bodies will change in ways that cannot be fully predicted. Their minds will be tested in ways that cannot be fully prepared for. Their connection to Earth will thin into a thread of time-delayed messages, stretching across a widening void, replies arriving with a delay that grows longer as the distance grows. They may never come back, not because the rocket does not exist, because after enough years at 0.38 G, their bones and their hearts may no longer tolerate the world they came from. Mars will have recalibrated them, quietly, irreversibly, without announcement. The real shock is not any single danger. Not the radiation, not the dust, not the cold, not the pressure, not the food, not the isolation, not the thin medicine. It is the way all of these combine into an environment where ordinary human life becomes impossible and is replaced by something else entirely. Something that looks less like settlement and more like permanent survival management. Less like a new home and more like a life support experiment conducted on hostile ground, with no control group, no exit protocol, and no guarantee the machinery holds. Mars does not hate us. It is not cruel. It is indifferent in the most absolute sense the word allows. Cold rock, thin carbon dioxide, ancient silence that predates life anywhere in the solar system. It resists habitation not from malice, but because it was never shaped by the forces that make habitation possible. No magnetic field, no thick atmosphere, no liquid surface water, no oxygen, no biology in the soil. A planet that shows what a world looks like when the conditions for life never quite came together, or came together once, and then drained away into the vacuum over billions of years. To live there would be to carry a bubble of Earth across the void and set it on alien ground, then maintain it by hand against everything the ground can throw at it. To spend days keeping the bubble intact, and nights sleeping inside it, knowing the seals are wearing, the filters are clogging, while the planet outside remains the same as it was yesterday, the same as it will be a million years after the last human leaves, or the last habitat fails. And to carry, beneath the daily routine of system checks and filter replacements and crop rotations and radiation logs, the quiet knowledge that you chose this, that you left behind a world that gave you everything for free. Air, water, warmth, sky, the sound of wind through living trees, and traded it for a world that gives you nothing and never will. The distance between those two worlds is not only measured in millions of kilometers. It is measured in the growing silence between messages sent home and replies that take a little longer each time to feel like they're coming from the same reality you once belonged to. That is what living on Mars would actually be. Not a new beginning on a new world. A permanent vigil inside a fragile machine on a planet that never stops reminding you that you were not built for this. That nothing you are was built for this. And that every breath you take is a small mechanical victory against a silence that has lasted longer than life itself.